Hello, and welcome back to Introduction to Genetics and Evolution. In the previous video, we looked at the types of selection that can operate on a single locus or single gene in that case, we looked at the effects of dominance, and in particular on directional selection. We talked about other forms of single locus selection, such as heterozygote advantage, which is overdominance, underdominance or heterozygote disadvantage, and negative frequency dependent selection. Now, if you go back, Darwin, of course, didn't know anything about genetics. He instead thought of natural selection in the context of variation in traits. And that's what a lot of breeders do when they're applying artificial selection to, say, their dogs or cattle or corn or whatever they may be using. Now, natural selection can be studied in the context of quantitative traits or in the context of single loci. Now, when we talked about in the context of heritability previously, we were thinking of it in terms of these quantitative traits. And you don't necessarily need to know the underlying genes to infer what kind of selection is operating. So let's talk about the types of selection that can be inferred when you're looking at phenotypes and changes in phenotypes over time, or changes in traits over time. This is a picture from the Freeman and Heron book, and this depicts three kinds of selection that I'll introduce to you. Directional selection. This is a little bit different than the previous directional selection we talked about when we were looking at a single gene thing. It's very unfortunate they happen to have the same name. But in this case, we're looking at selection which favors one extreme of the distribution over the other. So we have here in the top picture the number of individuals before selection, so it's a particular distribution. We have in the second graph the probability of surviving. So in this case, the ones that have the higher trait values have a higher probability of surviving than the lower ones. And then in the bottom part, we see the number of individuals having these different traits after selection. In this case, we see sort of a change in the mean. The mean here started just below 7. Here it's just above 7. So this would be directional selection. I'll introduce each of these in more detail in just a minute. We have one called stabilizing selection, where individuals with the intermediate value are favored. And we have disruptive selection, where individuals with the extreme values. Let's go over these in turn. So this first example is directional selection, and we're applying this in the context of phenotypes. We're not looking at the single gene version of it. And I apologize again, they tend to have the same name, which is very confusing. But again with this, individuals at one end of the distribution are favored. So if we imagine the x-axis here is height, let's say that's the trait value on there, then with this particular thing, then the probability of surviving is higher for those that are taller, whereas it's very low for those that are short. So what this will do is it'll change the mean of the population over time. The assumption here is that there's some heritability, that there's some heritable component to height, and therefore selection can induce this sort of a change. In this case, what you see is you see the shift over from a mean of just below 7 to a mean of just above 7 in this fictional example. Well, let me show you a real example. This shows change over time in pink salmon weight in Canada. So this is from two different places where pink salmon were caught several times. We see here that the average weight in 1951, 1952 was a little bit over 4 pounds. And we see over time, smaller and smaller salmon are caught. Same thing with the Upper Johnston trait. Over time, smaller and smaller salmon are caught. Now, this has been shown in pictures as well. Here's an excerpt from a magazine. This is showing collections from the same place over 3 time periods. Here's the 1950s. Look at the size of those fish. They're mammoth. The 1980s, they're pretty good. And in 2007, they're fairly small. What happens? Well, when people go fishing, they go out there, they catch the biggest fish, and those are the ones they take home and eat. Smaller fish are less likely to be caught or maybe more likely to be thrown back. So over time, there's been this selection for favoring smaller fish or for smaller fish. That is directional selection acting on the phenotype of size, in this case in pounds. Well, let's look at an example of another kind of selection. This is an example of stabilizing selection. Okay? This is the case where individuals in the middle of the distribution are favored, so they have the highest fitness. Whereas individuals near the ends have a lower probability of surviving. In this particular case, there's no change in the mean, but you actually end up losing some of the extremes. Well, there's a classic story that goes with this. In the late 1800s, a fellow named Bumpus lived up in New England, and he was interested in the sparrows that were found there. A big ice storm hit New England. Lots and lots of birds died. He went out there and brought back a lot of the birds that were sitting out there in the snow, not doing so well. And what he found, looking at these house sparrows, he brought in 136. 64 of them died and 72 survived. What he found is that the mean of the survivors and the mean of the dead was about the same, right? They were about 26 grams in size. In contrast, if you look at the extremes, all the ones that were more than 28 grams and all the ones that were less than 23 grams died. There were some that died that were intermediate there, but all the ones with extreme values died, so they had a lower probability of survival. Whereas the ones with the intermediate traits, they were more likely to survive. Well, there's a definite example of stabilizing selection that operates in humans. Can you think of what that would be? Something where the intermediate values are favored. Well, that answer is human birth weight. That again, when we tend to think of very small babies that are 2 or 3 pounds, their probability of survival is not very high. You know, an 8-pound baby, 9-pound baby, they have a pretty good probability of surviving. But when you get up to the 12, 13-pound babies, again, it goes back down. That, you know, a lot of them do survive, especially with medical intervention, but the probabilities tend to go down, especially if you have less medical intervention there. Again, individuals in the middle of the distribution are favored by natural selection. So this would be a case of stabilizing selection. I should emphasize, stabilizing selection is not the same as overdominance. Overdominance is something that happens when you're looking at a single gene. This is looking at a pattern in phenotypes. It's a common error. I just want to make sure to emphasize that. Last but not least, disruptive selection. This is basically the exact opposite of stabilizing selection. That individuals at the two ends of the distribution tend to be favored. Again, in this case, you have no change in the mean, even though you're losing those individuals that may have the mean values. But you have an increase in those with the extremes, both high and low, and you have a loss of the intermediate phenotypes. So you have basically a greater variance over time. There are examples of this. This is one that was published in the around 1992 or so. This is looking at beak size in African finch. And we found that, and what people found is that when you're looking at the females, they tend to specialize on 2 sedge species seeds. And those with particular bills, this set can specialize on one type, this set can specialize on another type. But the intermediate ones actually are not as good at either type of seed. So the intermediate ones here, the ones near the mean, are not as good. They have lower fitness. It is better to have one of the more extreme phenotypes. So those are, again, the 3 types of selection that you can infer from looking at phenotypes. Directional, where you have a change in the mean and one end is favored. Could be the other way too. Stabilizing selection, where the ones near the mean are favored. You lose variance. You lose those extremes. Or disruptive selection, where the intermediate ones are unfavored and you have an increase in variance, an increase in those extremes. Now, before we leave selection behind for this particular lecture, I'd like to close with a few final thoughts. So, is selection good or bad for a population? We tend to conceive of selection as being something bad. We tend to imagine this sort of struggle and some genotypes not being able to pass themselves on, some individuals being left out of the population, whatever species it is, we're looking at animals, plants. In fact, that's a very biased view. Natural selection is preferentially reducing or eliminating the bad genotypes. When I say bad genotypes, it's those ones that are not as well suited to passing along or producing offspring, right? So either they have a deficit in survival or they have a deficit in reproduction relative to other genotypes. As such, because we're getting rid of these so-called bad genotypes, the average fitness of all the remaining individuals in the population after selection actually goes up. That if you look at the people who are still there after selection's operated, on average they tend to be more fit. And the reason for this is that the bad alleles have been removed. And this is especially true when you're looking at simple directional selection. And ultimately this will lead to a long-term improvement of the population's ability to survive and reproduce. Now, in this regard, directional selection is improving the average population fitness, and the speed with which it does it has been described by Ronald Fisher, who's depicted here on this slide, in what's referred to as Fisher's fundamental theorem of natural selection. This is elaborated very nicely in his 1930 book, but he identified that the rate of increase in fitness under directional selection is equal to the genetic variance in fitness. And we could think of this as similar to the heritability aspects we talked about earlier, right? Selection acts on that aspect of the trait that has a genetic basis, right? That VG is what responds to selection out of the overall VP. So in terms of overall fitness, we see the same sort of concept applying. The rate of increase in fitness is equal to the genetic variance in fitness. So if there's a lot of variance in fitness, then you'll see large step changes in the overall average population fitness. In contrast, if most individuals have fairly similar fitness, you won't get that much of an increase in overall population fitness. So I just wanted to present that to you as a couple of closing thoughts because these are some neat ideas that have been around for quite some time. And I hope you enjoyed these lectures on natural selection. In subsequent videos, we'll look at another very important evolutionary force, but one that's far more random. We'll be looking at genetic drift. So stay tuned. Thank you.